integral the function that become infinite at the point within the interval of integration are improper integral type 2. So for example, if you have a function f of x and f of x is discontinuous at one of the endpoints. So say here this function, and let's say you have a vertical asymptote at a, and the function look kind of like this, and you want to calculate the integral from a to b, and so you want to talk about this area. Okay. Now notice that the since we have a discontinuous at a, well, I can have an arbitrary point c as c approaches a. So c can come as closest to a as possible but not be a. So then here I'm looking at the limit at c approaches a from the right hand side of the integral from c to b of f of x dx, and this is the same as the integral from a to b of f of x dx. Now similar case for number 2. Now number 3, if you have a discontinuous in the middle of the graph, we have a discontinuous right in the middle. So say you have a vertical asymptote, or maybe you just have a hole, your graph have a hole, okay, in the interval from a to b, and this is what I want to calculate, and I know I have this point here is discontinuous. I can choose a c where c is a where then c is the point that is in the middle here, right? And break that up into things. Now that I have now I break the integral into two things, I can take a look at, okay, what then I want to say I want to find the limit as, let's call d approaches c from the left, where that give me the area from the left, and the limit at d approaches c from the right, of course, of the integral, that two things that we're breaking up, right? So let's take a look at an example how this works. We want to evaluate the integral from 0 to 2 of x times ln of x dx. Well, we know that this integral is discontinuous at 0 because ln of 0 is undefined. So then I'll start this by start with the limit. I'll go ahead and say, okay, then the limit as a approaches 0 from the right, the integral from a to 2 of x ln of x dx. Yeah. Then I can use integration by part. I'll let u equal to ln of x, then du equal 1 over x dx. X, I will let dv equal x dx. So v equal 1/2 x squared. Then I'm looking at the limit, and this becomes the limit at a approaches 0 from the right of u times v that is 1/2 x squared ln of x. Evaluate from a to 2 minus the integral from a to 2 of v du, that is 1/2 times x dx. So this equal to the limit at a approaches 0 from the right side of 2 ln of 2 minus 1/2 a squared ln of a minus 1/4 x squared. Evaluate from a to 2. So the limit at a approaches 0 of 2 ln of 2, that is 2 ln of 2. The limit at a approaches 0 of 1/2 a squared ln of a, that is 0, minus the limit at a approaches 0 from the right of 1/4 times 4 plus the limit at a approaches 0 of 1/4 a squared. So that is 0 and 1. So then we have 2 ln of 2 minus 1. What happens when we have a discontinuous in the middle of the interval? So here we know that we have a discontinuous at 1, right? So let's go ahead and break this interval into 2 parts. Here we look at the integral from 0 to 1 dx of x minus 1 to the 2/3 plus the integral from 1 to 3 dx times x minus 1 to the 2/3. So I'm looking at the limit at b approaches 1 from the left of the integral from 0 to b dx over x minus 1 to the 2/3 plus the limit as a approaches 1 from the right, integral from a to 3 dx over x minus 1 to the 2/3. We will solve this using substitution, where u equal to x minus 1, du equal to dx. So then this integral becomes the limit at b approaches 1 from the left of 3 times x minus 1 to the 1/3. Evaluate from 0 to b plus the limit at a approaches 1 to the right of the same thing, 3 times x minus 1 to the 1/3. Evaluate from a to 3. So this is the limit at b approaches 1 from the left of 3 times b minus 1 to the 1/3 minus the limit at b approaches 1 from the left of 3 times negative 1 to the 1/3 plus the limit at a approaches 1 from the right of 3 times a minus 1 to the 1/3. Excuse me, as 3 first. 3 on top, 3 minus 1, that is 2 to the 1/3 minus the limit at a approaches 1 from the right of 3 times a minus 1 to the 1/3. So here that we can see that the limit at b approaches 1 from the left of 3 times b minus 1 to the 1/3 and minus the limit at a approaches 1 to the right of 3 times a minus 1 to the 1/3 that will equal to 0. So now here, what do I have left? Well, then this meant, well, this go to 3. And here I have 3 to the cube root of 2. So this is the result of the integrand. We can, so a lot of time we have function in which we can't really calculate the integral directly. So if we can compare the integral with another integral in which we know the result of, then we can have a good idea of what the value of the integral look like, or how's that integral behaving. Okay, so let's look at the comparison theorem. Let f of x and g of x be continuous function on a to infinity, with f of x is less than g of x and greater than 0 for all a in the interval, for all a that is greater than 0. Then if the integral from a to infinity of f of x dx diverge, then the integral from a to infinity of g of x is also diverge. Right? So if the function that is smaller diverge, then the function that is bigger also diverge. But if the larger function is converge, then the smaller function gonna be converge. Okay? If the positive function f and g are continuous on the interval a, b, the limit at x approaches infinity of f of x divided by g of x convert to a value L, then both f of x and g of x either both converge or diverge. Okay. Take a look at the first problem. For what value of p does the given integral converge? When the integral does not converge, and what is its value? Okay, so start with this integral. Well, let's make it into different cases. So let's call case 1. What if p is not 1? Okay, when p is not 1, I'll have this integral from 1 to infinity of dx over x to the p equal the limit at b approaches infinity of the integral from 1 to b of dx over x to the p. This is the same as the limit at b approaches infinity of 1 over 1 minus p times x to the negative p plus 1. Evaluate from 1 to b. And this is equal to the limit at b approaches infinity of 1 over 1 minus p times x to the negative times b to the negative p plus 1 minus 1 over 1 minus p times times 1 to the negative p plus 1. So let's clean this up. Well, I can factor out the 1 over 1 minus p, and this is times the limit at b approaches infinity of b to the negative p plus 1 minus 1. So let's say what happened when p is greater than 1. So let's take a look at this case when p is greater than 1. Yeah, when p is greater than 1, then this becomes one over 1 minus p times the limit at b approaches infinity of b to the negative p plus 1 minus 1. If p is greater than 1, then this just become this become 1 over 1 minus p, gives me equal p minus 1 here. Yeah, because if p is greater than 1, then the term b to the exponent negative p plus 1 go to 0, right? And so we have the negative 1, so we multiply it out. What if for p is greater than 1 here? So what happens when p is less than 1? When p is less than 1, then the term b to the negative p plus 1 go to infinity. So then we're looking at infinite. Then we're looking at infinite here. So this go to infinity for p is greater than 1. Excuse me, for p is less than 1. Okay. So then I can say that, all right, that's the case. Then this integral here convert when p is greater than 1 and diverge when p is less than 1. What happens when it's equal 1 then? Well, if it equal 1, case 2, if p equal to 1, then I'm looking at 1 to the infinity of dx over x equal the limit at x, as b approaches infinity, integral from 1 to b dx over x, where the limit at b approaches infinity of ln of x evaluate from 1 to b. This is the limit at b approaches infinity of ln of b minus the limit at b approaches infinity of ln of x. And this convert to, and when p equal to 1, this is go to infinity. Okay. Well, so here we will use the comparison theorem, show that the given integral is converged. Well, we given f of x equal x squared sine square of x divided by x squared. Well, in order to show that this is converged, we have to show that this function is less than another function that is converged. So I can use the fact that, all right, sine squared of x is going between 0 and 1. This means 0 over x squared have to less than equal sine squared of x divided by x squared less than equal 1 over x squared. So then I let f of x equal sine squared of x over x squared, g of x equal 1 over x squared, and we can see that f of x is less than or equal to g of x. Well, the integral from 1 to infinity of 1 over x squared dx is convergent. So then f of x is also convergent. Now take a look at the next one. Well, we have cosine of x from the interval from 0 to pi over 2, and here we have a discontinuous of 0. Okay, I know that cosine of x is going between -1 to 1. So then here I have -1 over square root x less than or equal cosine of x divided by square root of x. So cosine, so here I have 1 over square root of x. Then here, well, I have f of x is less than or equal g of x here in this case. And we're looking at the integral from 0 to pi over 2, so -1 over square root of x is, so square root of x is a positive number. So here we get f of x is less than g of x. Okay, so we can guarantee that. So then here, well, I know that 1 over square root of x is converged. In the interval 0 pi over 2. So then f of x is also convergent in the same interval.